So, we have discussed the first and second law of thermodynamics, and while discussing the second law of thermodynamics, we talked about entropy, a very important concept, because the driving force of a reaction is largely dependent upon the entropy. And we demonstrated last time that the direction of spontaneous process is in the direction of generation of more disorder. Today in this lecture, we will extend the discussion on entropy. It is very important to understand entropy change in the system, entropy change in the surroundings, because it is directly connected to the spontaneity, to the feasibility of a process. So, let us first discuss some basics, and then we will move on to some applications, including some numerical problems. The second law of thermodynamics says that the entropy of an isolated system increases during the course of a spontaneous process. That means, if we want to make a general statement that what should be the sign of entropy change in the system plus entropy change in the surroundings. So, if I combine these two, I will write these as entropy change in the system plus entropy change in the surroundings, I will write greater than or equal to 0. Why I am writing greater than or equal to 0? Because if the process is irreversible, is spontaneous, then ds system plus ds surrounding has to be positive by the second law of thermodynamics, and equality applies to reversibility. So, whenever the process is reversible, we will use equal to sign, and when the process is spontaneous or irreversible, we will use greater than sign. Now, let us say that the heat change is dq for the system. This is the infinitesimally small amount of heat which is either given out or taken in by the system. And hence, if there is a thermal equilibrium between system and surrounding, let us say at temperature T, then the heat change for the surroundings the heat change is going to be minus dq, because if this is for the system, then the surrounding will be with a negative sign. And let us recall the discussion of the previous lecture. The heat change in the surrounding divided by the temperature is equal to the entropy change in the surroundings. That means, this is entropy change in the surrounding. Now, let us take a look at the slide. As I mentioned that in general, we can write ds system plus ds surrounding is greater than or equal to dq by t, and this equation comes by substituting ds surrounding into this equation. According to this, ds system minus dq by t is greater than or equal to 0. From this general equation, that is by the second law of thermodynamics, ds system plus ds surrounding is greater than or equal to 0, I am going towards deriving another equation. And now, if I rearrange this equation, then I get the equation ds system is greater than or equal to dq by t. This leads to the equation ds system is equal to greater than or equal to dq by t. That is what is mentioned on the slide, and this is called Clausius inequality. That is, the entropy change in the system in general will be equal to or greater than dq by t. And here again equality applies to reversibility and greater than sign applies to irreversible or spontaneous process. This Clausius inequality is very important, because by using Clausius inequality we can get qualitative answers to several questions. Qualitative in the sense that if I know the sign and magnitude of dq, I can talk about how much will be or in which direction will be the entropy change of the system. So, that is why the conclusion written on the slide is that this Clausius inequality is very important in getting qualitative answers for change in entropy. So, what kind of qualitative answers we can expect from Clausius inequality? Clausius inequality is ds. If I am not writing surroundings, that means we should understand ds means entropy change in the system is greater than or equal to dq by t. The question is comment on the entropy changes in number 1, adiabatic irreversible expansion of a gas. Adiabatic irreversible, irreversible means I will use greater than sign. So, then I will write ds is greater than dq by t, because the process is irreversible, I am using greater than sign. And since the process is also adiabatic, adiabatic process means dq has to be 0, no exchange of heat between system and surroundings. So, the answer is ds is greater than 0, because dq is 0. You know, this is a common mistake which many times I have seen while discussing with several students, that whenever we say adiabatic process, generally one tends to consider that since there is no exchange of heat between system and surrounding, therefore, in each case the entropy change should be 0. No. Clausius inequality, this one, Clausius inequality gives qualitative answers. You see here the process is irreversible. So, therefore, I use greater than sign, and since the process is adiabatic, I put dq equal to 0. So, ds is greater than 0, and this is the driving force for the process. This is a different question, that how to calculate this change in entropy, we will deal with it separately. Now, let us take a look at the second comment, adiabatic reversible expansion of a gas. Now, let us consider the reversible case. Once again, I will start with the Clausius inequality, ds is greater than or equal to dq by t, and if the process is reversible, that means I will use equality sign. So, ds is equal to dq reversible by t. See, this is the same equation that we derived last time, that in order to calculate the change in entropy, we must connect the path by a reversible manner. And since the process is adiabatic, there is no heat exchange between system and surrounding. So, I have to substitute dq equal to 0. That means, if the process is reversible, there will be no change in the entropy. Irreversible process, the entropy change was positive. Reversible process, you see the entropy change in the system is equal to 0 under adiabatic conditions. So, that is what I meant by saying that the Clausius inequality quickly gives us qualitative answers to several questions. Let us move ahead and prove again by Clausius inequality that the gas expansion into vacuum is spontaneous. How do we approach that? Spontaneity in terms of entropy will be commented upon based on the entropy change in the system plus entropy change in the surrounding. If we want to comment on the spontaneity of a process in terms of second law of thermodynamics, we must calculate the entropy change in the system and we must calculate the entropy change in the surrounding. And if that turns out to be positive, then the process is spontaneous. So, here the question is to show that gas expansion into vacuum is spontaneous. The first thing is we need to calculate the entropy change in the system. So, let me go back to the Clausius inequality, ds is greater than dq by t. Expansion into vacuum means expansion against P external equal to 0 is a spontaneous, is an irreversible process. So, I will use ds is greater than dq by t. And if you remember, we also demonstrated last time that when a gas expands in vacuum, it is simultaneously both isothermal as well as adiabatic. I repeat, when a gas expands in vacuum, it is simultaneously both isothermal as well as adiabatic. Now, if it is adiabatic, I will immediately put dq equal to 0. So, that means ds. Now, let me write system is greater than 0. At the same time, ds surrounding, which is always defined as dq surrounding by T, the actual amount of heat transferred to the surroundings. And since there is no exchange of heat between system and surroundings in adiabatic process, this has to be equal to 0. So, ds total will be equal to ds system plus ds surrounding. This is greater than 0, this is 0, that means overall this is greater than 0. And by the second law of thermodynamics, if the entropy change in the system plus entropy change in the surrounding turns out to be positive, then the process will be spontaneous in that direction. So, hence we prove that the gas expansion into vacuum is a spontaneous process. The next question is show that cooling, which is transfer of heat from hot to cold, is spontaneous. So, here also we need to show that the entropy change in the system plus entropy change in the surrounding is positive. So, let me consider that the hot body is the system and cold body is the surrounding, and the amount of heat transferred is, let me take the magnitude, is Q. And when there is a transfer of heat from a hot body, it is losing heat, right. So, therefore, entropy change will be equal to, it is losing minus this much amount of heat divided by Th. Th is the temperature of the hot body. And if I consider the cold, wherever the heat is going to, that as the surrounding, then it will be plus, because heat is being received there, divided by Tc. Tc is the temperature of the cold body. So, overall, now if I say ds total, this plus this will be equal to minus Q by Th plus Q by Tc, or what we get is ds total is equal to, let us take Q out, and inside we have 1 over Tc minus 1 over Th, and obviously from here you see, since Th is greater than Tc, then that means this whole quantity is greater than 0. So, we show here that ds total is greater than 0, because Th is greater than Tc. And again, by the arguments of the second law of thermodynamics, here we again demonstrate that the cooling, transfer of heat from a hot body to a cold body is spontaneous. So, once again emphasizing on how to prove that a given process is spontaneous in terms of second law of thermodynamics, we need to show that entropy change in the system plus entropy change in the surrounding is greater than 0. We will need to calculate the entropy change in the system, and we will need to calculate entropy change in the surroundings, add up the both. If it turns out to be positive, then the process is spontaneous in that direction. Now, let us look at some specialized cases. Isothermal expansion of perfect gas. We want to derive an equation to calculate entropy change when there is an isothermal pressure volume change for a perfect gas. So, what we will do is, we will start with the definition of change in entropy. ds is equal to dq. Remember that we always have to put subscript reversible divided by the temperature. This is the general expression. Now, let me use the first law, du is equal to dq plus dw, and since we are dealing with isothermal expansion, isothermal case, the internal energy does not change. Isothermal means du is equal to 0. So, therefore, what I have is dq according to this equation, if I put reversible sign, is equal to minus dw. Let me again use reversible, and dw is minus pdv. So, it becomes plus pdv. In other words, dq reversible is equal to, here P, use the ideal gas equation, PV is equal to nRT. So, P is equal to nRT dV by V. This is what we get, and this I will now substitute over here, and let us see what do we get. What we get is ds is equal to n r t by t dV by V, which is equal to n r dV by V. And now we are ready to calculate the entropy changes. Since ds is equal to dq reversible by t, here we will see, and for a finite change delta s will be integration of dq reversible by t, and as we just showed that q reversible is equal to nRT and what we show here is now I integrate here and I integrate from V I to V f. So, what we get is the equation, or I can write here, is equal to n r log V final over V initial. So, what we have derived now is, let me write on a fresh page, is that delta S is equal to n r log V final over V initial. This is the expression or equation to be used for calculating the entropy change in the system when the gas expands under isothermal conditions. There is also point to be noted that there is no temperature appearing. Although we are saying it is an equation to be used for calculation of entropy change under isothermal conditions, but actually in the expression there is no temperature appearing. And if V final, expansion means V final is greater than V initial, that means logarithmic term is positive. So, during expansion delta S is positive and entropy will increase. Therefore, according to this equation, the increase in entropy does not depend upon the temperature, but it will depend upon the values of V f and V I. Another point to be noticed here is that since entropy is a state function, therefore, delta S is going to be same as long as the process is isothermal, whether it is reversible or it is irreversible. So, as long as the process is isothermal, it does not matter whether it is reversible or irreversible, we are going to use the same equation to calculate the entropy change when the gas expands from a initial volume of V I to a final volume of V F. Now, let us take another special case of entropy of phase transitions. What is a phase transition? A phase transition is a transition at which the phase of a system changes, the state of a system changes from one phase to another phase. An example of phase transition can be melting of ice, where water changes from ice to liquid water. And as we can see in the slide, that at transition the two phases are in equilibrium. That means, if I talk about any substance A and this is in the solid form at any temperature, let us say at its freezing temperature, and it melts, A goes to liquid form at freezing temperature, this is a phase transition. And phase transition is a reversible process. But what is happening here is, it is only the molecular order changing. Going from solid to liquid, the order is decreasing. If it is reverse, going from liquid to solid, the order is increasing. So, there is a change in the degree of molecular order. Since the process is reversible, occurring at constant pressure, so whatever is the change in heat, since it is at a constant pressure, this is equal to dH, or I will say Qp is equal to delta H, which is at a temperature Tf. Another property of phase transition is that whatever heat is supplied, that is used to change the phase of the system. In changing from solid to liquid, it does not change the temperature. You know that the transition takes place at a single temperature, unique temperature, that is whatever is the phase transition temperature. So, therefore, if I now write ds is equal to dq reversible by T, or if I write delta S as integration from initial to final dq reversible by T dt, so once I have ds is equal to dq reversible by T, then delta S is equal to q reversible by T, and at phase transition I will write delta S of transition, this is equal to delta H of transition, Qp is equal to delta H divided by the transition temperature. This is how you calculate the entropy change in the phase transition. And by looking at this equation, the sign of delta H will decide whether the entropy change will be positive or negative. For example, freezing is exothermic. Exothermic is delta H is less than 0, is negative. So, freezing means delta S should be negative. It makes a sense because in freezing the molecules become more ordered. So, therefore, the entropy change will be negative. Vaporization is endothermic. Vapors, liquid form goes to vapor and molecules have more degrees of freedom, and delta H is positive. Therefore, delta S is also positive. That means, the disorder increases upon vaporization. So, delta S is positive. Let us take a look at this table. In this table, the values of entropy of vaporization for several liquids is given. And if we notice in the first 4 rows, the value is approximately near 85 joules per Kelvin per mole. For a variety of liquids, this value is about 85 joules per Kelvin per mole. And this observation for a wide range of liquids, the standard entropy of vaporization is approximately 85 joules per Kelvin per mole is Troughton's rule. The reason for this is that for a variety of liquids, when these are vaporized, almost the same amount of disorder is generated. Whereas, if we take a look at the value of for water, you see water value is about 109.1 joules per Kelvin. This is much higher than 85, and the reason for this is that in liquid water there is an extensive amount of hydrogen bonded network, and therefore, when water liquid is converted to water vapors, that hydrogen bonding is broken and a large amount of disorder is generated. That is why for water the value is 109, it is much more than what is predicted by the Troughton's rule. Another deviation here is methane. Methane value is plus 73.2, and the value for methane is low. A part of reason is the low standard entropy of vaporization assigned to the low value of the entropy of the gas itself. That is, the gas itself has a small amount of entropy, it is low entropy, and this is connected with moment of inertia. These you will study later on. We have already discussed for water, the value is high because of a large amount of generated disorder as a result of breakage of extensive hydrogen bonded network. The entropy change for phase transition, this is very important, not only in discussing the phase changes in solid, liquid vapor, etc. The phase change can be within the solids also. For example, carbon graphite converting to carbon diamond, that is a phase change. When we talk about even biological system, a protein from its native structure goes to an unfolded structure, that is also a change which is like a phase change. A nucleic acid unfolds, that is also like a change which can be treated as a phase change. So, in those cases we will later on demonstrate through several applications and several numerical problems that it is possible to calculate the value of entropy of phase transition, and then this value can be used to connect various thermodynamic parameters which are very, very important in predicting the feasibility, spontaneity of a process under the given conditions of temperature and pressure. we will continue our discussion on entropy further and connect these various basic principles that we have discussed with applications. Thank you.